So the second hyperbolic function, a real second hyperbolic function, cannot be the solution to a complex differential equation like this, right? But it turns out you only need to make a very slight adjustment, okay? Previously, we assumed the steady state solution A of t is A0 times second hyperbolic of t over Tp, okay? Now, our differential equation is complex. You just need to make a small adjustment here. Previously, it's power of 1. Now, it's power of 1 plus j beta, okay? Your exponent is generalized from a real number, 1, to a complex number, 1 plus j beta. Of course, beta is a new unknown constant to be solved. Okay. So this is true, and actually you can try to calculate the corresponding amplitude and the phase of this function, okay? Because this is not a standard envelope and the phase representation, okay? A second hyperbolic function to the power of 1 plus j beta is not standard form. But this is standard form. It turns out that the amplitude is the same as before, second hyperbolic function of t over Tp, and the phase is unconventional one, beta coefficient times natural logarithm of second hyperbolic of t over Tp. Okay, so this is the standard representation. I know the formula might not make sense for you, so I draw some curves for your convenience. The blue one means the power, which is absolute square of A of t. If you take absolute square, the phase term disappears, right? So all you have is A0 square, sec square. So this is represented by the blue curve. Okay? The peak value is A0 square. And the FWHM is roughly the Tp parameter. How about the phase? The phase is this one, right? Beta times log of second hyperbolic function. If you look at this formula, you might have no idea what's the curve, right? But if you plot it, it's not difficult. Just a red dashed dotted curve, phi of t. Pretty like a parabolic curve, right? But actually, it's not parabolic. It's determined by this formula. And the one thing I have to emphasize is the red curve here is based on the assumption that the beta parameter is negative, okay? Beta is less than 0. But a negative beta actually means upchirp. So you have a closely parabolic curve with positive curvature. Okay, so it's not intuitive, but just remember, positive beta means downchirp. Negative beta means upchirp under this symbol system. Peak power, pulse energy, average power are nothing to do with the phase. So all these three formulas are the same as what we have seen in the previous section. The other thing is, what is the corresponding instantaneous frequency shift, which we have learned before. If you have a nonlinear phase curve like the red one, if you take first order derivative, you got the nonlinear frequency shift. Okay? Frequency shift is a function of time. So in this situation, after the time derivative, you got this. You have basically a tangent hyperbolic function, tanh function, represented by the gray dashed curve. Okay? And as you can see, this is a monotonically increasing curve. So the instantaneous frequency increases with time. So this is an upward pulse, right? So although the formulas look formidable, but if you draw them, they are just very simple, smooth curves, okay? So remember, in steady state solution, you got intensity distribution like this, a very simple phase, and monotonically increasing instantaneous frequency. Then, as we did before, now we need to substitute the complex second hyperbolic solution into the master equation, okay? And if you do so, you can get two complex equations for 4 unknowns, okay? What are the unknown constants we intend to solve? A0, Tp, beta, and the psi, okay? What is A0? Your amplitude, okay? What is Tp? Your pulse width. So these two are what we have seen before. But now we have 2 extra unknowns. What is beta? In our assumption, beta is here. Basically, it describes the chirp rate. The bigger the beta, the stronger the pulse chirp. Or equivalently, the curvature of the red curve is about beta. And the frequency change, instantaneous frequency change, is about beta. So beta determines your phase or your instantaneous frequency change. And what is psi? Psi is not here, right? But psi is in the equation. That is the CEP shift in your laser system, okay? 所以这个微分方程其实不是很传统的哈，所以我给你一个所有的参数都已知的方程式，你去找个 unique solution 不是，你这个方程式就变成跟解绑在一起了啊。解找出来的同时，方程式的某个参数也被找出来了。So you might have some experience about this type of mathematical problems, the eigenvalue problem, right? What is eigenvalue problem in linear algebra? Matrix A times eigenvector x equals eigenvalue lambda times eigenvector. Okay. So you have to solve both eigenvalues and eigenvectors together. Okay. 这里有点这种味道哈，就是你这个方程式本身有个参数，不是事先给你的，是找解的过程一起找出来的。Okay. And it's here. So you have 4 unknowns, but we have, it looks like we have only 2 equations. The situation is very similar, similar to the previous section, because after substitution, you have second order time derivative, absolute square times the unknown function itself. So after substitution, you have only 2 possibilities. Either related to sech to the power of 1 or sech to the power of 3. But previously, you have no imaginary part. Now you have. So either sech to the 1 plus j beta or sech to the 3 plus j beta. It's a generalization. But only 2 possibilities. And the first function, sech to the 1 plus j beta, has a coefficient function, big A, a function of 4 variables. These 4 variables are the 4 unknowns we need to solve. And the sech to the 3 plus j beta has a coefficient, big B, again, as a function of 4 unknowns. Okay? So to make this one equal to 0 always, regardless of time instant t, the only possibility is both big A and the big B functions are zeros simultaneously. Okay? So we have equations 1 and 2 here. We have 4 unknowns, but we have 2 equations. But don't worry, these 2 equations are complex equations. So each one actually corresponds to 2 real equations. Real part equals 0, imaginary part equals to 0. So equation 1 alone actually gives you 2 real algebra equations. Similarly, equation 2 gives you another 2 real algebra equations. So you got 4 algebra equations. So it's sufficient to solve the 4 unknowns uniquely. Okay. And now it's not very easy to use the graphical solution approach as we did in section 4-2, because now we have 4 real equations instead of 2. Okay. If you have only 2, just 2 curves, intersection point should be the solution. But now you have 4. So it takes a lot of effort. So I will skip the mathematical solution details and trying to show you some simple conclusions based on the numerical simulations. Okay. So this slide focuses on the effects of group delay dispersion alone and assuming there is no cell phase modulation. Okay. Remember, in this section, what is new compared with the previous section? Now we include the phase modulation. Okay. So the 2 most important phase modulation effects are group delay dispersion and the cell phase modulation. So we have 2 knobs to play with. If they appear simultaneously, things could be relatively complicated. So the best way is, why not just tune one of the 2 knobs first to see the impact, then tune the second knobs only, and eventually tune the 2 knobs together. Okay. So this is what I'm trying to do. First, we assume there is no cell phase modulation. So delta coefficient is 0, only focusing on what happens when your group delay dispersion changes. Okay. So I use the computer simulation, actually just trying to solve equations 1 and 2 numerically. And I plot, in the first figure, I plot the steady state pulse width versus the GDD. Okay? And I use 2 colors to highlight anomalous dispersion, then big D is negative, and the normal dispersion, big D is positive. Okay? And at the middle, it means no GDD. Okay, 0 dispersion. In the second figure, I plot the steady state bandwidth, it's a frequency domain information, versus, again, the GDD parameter, from anomalous to normal dispersion. The third one, I plot the chirp rate beta coefficient versus the GDD. Okay. So what information could we obtain from these 3 curves? Okay. For example, at 0 GVD, your big D coefficient is 0. You got minima pulse width. If you check the blue curve, right? Where is the minima point? Here. And it occurs when GDD parameter is 0. Okay. You got the maxima bandwidth, because if you look the red curve, where is the maxima? Here. And it occurs at 0 GDD. Okay? And you also have chirpless steady state pulse. If you look the green curve, when GDD is 0, your beta parameter is also 0. So D equals 0, beta equals 0. And we know if beta equals 0, it means chirpless. The pulse has no chirp. Okay. So if GDD is 0, you got minimal pulse width, broadest bandwidth, and a 0 chirp. But actually, this happens to be the case of section 4-2, right? 又回到前一节的例子，什么 phase modulation 都没有。OK， 所以这本来不是我们最想知道的嘛，因为这个前一节就看到了。我们想知道的是 ，what happens if there is GDD? And by these three figures, we can conclude as dispersion magnitude, the absolute value of big D parameter increases. The tendency is quite clear. Your pulse gets broader because the blue curve will increase on both directions. Okay? 从 zero GDD， 不论你是往 normal dispersion 增加，还是往 anomalous dispersion 增加，结果都是造成你的 steady state pulse 变胖。Okay? And your bandwidth is reduced. Okay? As your GDD parameter increases, either to anomalous direction or normal direction, your bandwidth is reduced, always. And your chirp rate will also increase, okay? But it's asymmetric, right? If your GDD parameter is more and more negative, your beta coefficient is more and more positive. But as I emphasized before, a positive beta means down chirp. That means steady state has more and more serious down chirp as big D is more and more negative, which is intuitive, right? 我的材料的辐射散越来越严重，那我 steady state pulse 就会带着越来越大的 down chirp， 这两个本来就是一致的。On the other hand, if your material dispersion is more and more positive, your beta coefficient is more and more negative. That means your pulse has stronger and stronger up chirp, which is also natural. Okay? So the simulation results are not surprising. Okay? 一切都如预期。一旦我的色散放进来考虑 in general 造成的结果 pulse width 变胖 bandwidth 下降 steady state pulse 不再是 chirpless 它会有 either up chirp or down chirp but consistent with the material dispersion you introduce. Okay. Any question? But if you are very careful, please focus on, in addition to the qualitative description, maybe you can pay attention to quantitative information. For example, minimal pulse duration here is about 330 femtoseconds. If your GDD parameter increases to the maxima in this simulation, your pulse width increases by how many times? This is 330 femtoseconds. Here it's about 250 picosecond. This is 2.5 picosecond. 所以你把色散的量从0增加到这边是6个单位的时候，你脉冲宽增加了多少倍？你就用 2.5 picosecond 除上330个 femtosecond， 大概多少倍？7倍多吧。Okay. So remember the number. The pulse duration increases by a factor of about 7. How about the bandwidth change? Intuitively, if your pulse duration is broader, your bandwidth is narrower, right? But it's qualitative description. How about the quantitative description? Here, the maximum bandwidth is about 1 terahertz, but the minimum bandwidth is about 0.5 terahertz. So what's the difference? the bandwidth is reduced by about a factor of 5. Okay, so here the pulse duration increases by a factor of 7, but bandwidth is only reduced by a factor of 5. 7 is bigger than 5, so what is the problem? Good. The answer is it's no longer chirpless. 你的脉冲展宽的程度超过频宽的缩减量，意思就是我频宽才缩5倍啊。本来如果一切都是 chirpless， 我的 pulse duration 应该也只展宽5倍而已。它为什么展宽到7倍之多？超额的展宽。Because now you got some chirp, and the chirp will increase your pulse width. It's not manifested by your bandwidth information. OK， 所以剩下来的那2倍就是用 steady state, you got extra chirp 来解释。